Everyone. We have a press briefing today about a newly published research article about permafrost thaw and ice wedge thaw that appears today in the journal Nature Geoscience. A handful of researchers who worked on this study are here to discuss it. We have Anna Liljedahl. She is with the University of Alaska Fairbanks Water and Environmental Research Center, and she's the lead author of the study. Ronald Donnan is with the Alaska Division of Department of Natural Resources. He's with the Division of Geological and Geophysical Survey. Ken Tape is also a research assistant professor with the UAF Water and Environmental Research Center. And Vladimir Romanovsky is a professor with the UAF Geophysical Institute. If you'd like to start, Anna, with a summary of your research. Thanks.
Thank you, Jeff. Yes, so today our article came out, which shows that ice-wedge degradation and melting ground ice is reshaping the Arctic landscape. And this is happening not just in Alaska, but also Canada and Arctic Russia as well. And we're seeing this happening fast, with under a decade, with dramatic changes to the topography of the landscape. And these changes are...
Can you turn your mic on?
Oh, yeah. Should we start over?
Yeah, please.
It's good I get to practice.
Yeah, it's
We all have our mic on, yes.
It's on.
Okay, yeah, thank you everyone. So we are today, our paper came out today that shows that melting ground ice and ice wedge melting is reshaping the Arctic landscape. And this has dramatic impact on the hydrology of the Arctic. So I would consider it a tipping point for Arctic hydrology, where we are now seeing resulting in much more runoff into the rivers and the lakes, and the landscape generally becoming drier, even if the precipitation remains the same. And these changes, we're seeing them happening relatively fast. Like, we usually talk about glaciers as the canary in the coal mine when it comes to Arctic impacts of climate warming in the Arctic, but I think here we're seeing dramatic changes to the hydrology within under a decade. So even an individual summer can cause changes to the landscape that increases the runoff into the Arctic Ocean and so on. And another thing too is these changes are happening in permafrost that is very cold, down to minus 14 Celsius across the landscape. And permafrost warming has been gradual, happening across the recent decades, but we're showing changes to the topography within a couple of years. And we've seen this changes by combining field observations. So me and my co-authors, we've been to all of these sites and observed mismatches in vegetation and soil moisture, and also changes in vegetation, as well as ponds forming or ponds disappearing, and also just subsidence in the landscape. So some areas are sinking in, so on. So this, I think, why do we care about this? Well, if we increase the runoff from the Arctic landscape, where we have these ice-wedge polygons, that can affect sea ice growth. We could see more sea ice growth because sea ice is fresh water and we're putting more fresh water into the Arctic Ocean. Or we could see a decrease in sea ice growth because we have more warm water entering the Arctic Ocean. Another thing is the changing in soil moisture and surface wetness can affect the carbon fluxes. And we all read a lot about carbon fluxes from the Arctic and how it affects the global climate. So here we could either create more warming or less of a warming impact. And I think something else too, these regions of the Arctic are breeding grounds for a lot of migratory birds that travel thousands of miles. And they really like these shallow pools of water. But when we degrade these ice wedges, we drain these pools of water. So these birds might have a hard time finding their favorite breeding grounds. And lastly, I also want to point out that people living in the Arctic, in the early fall or early winter, the tundra travel might become more cumbersome because it's so much easier to drive snow machine across a flat landscape than it is driving snow machine across a landscape with a bunch of mounds and a lot of up and down topography. So they might have to add another hour or two when they go and visit their families. So I think I'll leave over to some comments maybe from.
Can you expand a little on what ice wedges are and how they're formed in the tundra and how they're a feature of northern topography?
Yeah, so these ice wedges, they form over hundreds, if not thousands of years of frost cracking in the soil. So when we have really cold winters, the soils are cracking and form a crack in the ground that could be several meters down into the ground. And when the spring comes and the snow melts, the snow melt water infiltrates into these cracks, and then it refreezes. And if you repeat this process hundreds of times, thousands of times, suddenly you've built this massive wedged ice body that could be 10 meters wide at the top and 15 meters deep down. And it's pushing the soil, and the only way the soil can go is up. So that can create these ridges above these ice wedges. And so the landscape is kind of represented by a bunch of small shallow pools of water because of these ridges. And when we have a disturbance to the ground surface like fire, but in our case we were showing that we have melting of these ice wedges from the top just by having warmer summers, then suddenly the ground subsides above these ice wedges. So now the water can drain off. And you can kind of imagine, I was thinking, how do I explain this to something maybe we see every day who are not living in the Arctic? And imagine like if you bake muffins, you have this muffin pan, but you don't have any muffins in it to begin with. So it's like all these little hollow spots. And that's kind of how the landscape look like when you're growing these ice wedges.
Muffins, it's low center polygons. And then it turned into the cook thing.
Yes. Yeah, exactly. He got So when you make the muffins, that's how the landscape looks like with this
muffin itself.
Yeah, muffin itself. So that's the switch in landscape. No muffins, two muffins.
All right, thank you. I should mention that a summary of the study is on the new UAF News website at uaf.news.edu. Up next, we'll have Ronald Donnan to talk about his contribution.
Yes. So my job at the state is to quantify groundwater, and this study is relevant in the sense that in cold areas like continuous permafrost, there isn't much groundwater that is usable. So fresh water is only really present in taliks, which are thawed zones that are connected to the surface, because they get fresh water from precipitation. And this study is relevant because, as Anna said, we have less evapotranspiration and more runoff, so a bigger portion of the water is actually present in the waterways. And this allows the streams, the creeks, and the rivers to remain open longer during the season and prevent freezing of the gravels that potentially could harbor groundwater resources. And so in the end, when the warming progresses, I think the amount of groundwater is actually going to increase in the Arctic. We'll see more deeper taliks forming in many places. And the other things that are important for the state are also fisheries and some of the migrating animals like the caribou that are of interest. How is this whole process going to affect them? And although that's not my field of study, but Yeah, and so my contribution to the study was also the thermal aspect of the modeling. So there's a whole modeling component attached to the study, and I was involved with doing those simulations.
All right, thank you. I was close on the website, but not quite. It apparently is news.uaf.edu, where the summary is. So next we'll hear from Vladimir Romanovsky.
Okay, so I think I would like to first make a couple points, maybe 3 points, which maybe not exactly in the paper, but it's what I can kind of get out of it. So first of all, and Anna already mentioned it. So when we model permafrost and changes in permafrost for the next 100 years, we see some, we color red where permafrost is thawing and degrading, and blue is a stable and still low temperatures. And when you show these maps with lots of blue in the very high Arctic, the impression is, well, everything is good there. It's stable, and nothing will happen there till when it turns into some, at least kind of pink color, right? Well, it's not exactly right, and this research and publication exactly showing it. So you don't have to wait when temperature in permafrost will cross this 0 degrees threshold. Even in very, very cold permafrost environment, these processes can start, and they're already happening. That's what actually documented. Simply because you don't have to trigger this long-term and kind of widespread permafrost thawing to have all this. You just need to increase the summer thaw layer to get into ice, and it's already enough. So as soon as that happens, ice melts, turn into water, run away, surface sinks, and you have all this, nice, turn upside down or inside out muffin, right? So that's one point I would like to make. So it's just sometimes wrong impression that cold permafrost is stable and nothing will happen. So it's not true. So the second point was what was my second point. So it's also important not only for ecosystem, what already we heard, that it's very important for infrastructure as well. So all these changes are not only make difficult to local people travel or to creatures who live there, continue to live, but it's also very big impact on infrastructure, whatever it is, roads, pipelines, buildings. So, and in this case, actually, there is not only warming in climate, but also infrastructure itself make combined effect and make permafrost even less stable than it's happening in the natural conditions. Let's see. In terms of what is my part was we provided at one of the sites we provided temperature measurements, which actually in the ground, which actually explain exactly the situation that even permafrost is still very cold and very low temperatures, active flare, the seasonal thaw or summer thaw, for a few years in a very high Arctic was about 15 centimeters deeper than it was normally occurred. And it was enough to trigger these processes in a very, very cold permafrost. So that's another kind of very good point that it could happen just after 2 warm summers. Again, you don't have to, it's not linear process. You don't have to wait long. If you have, for reason of generally warmer climate, 1, 2, 3 very warm summers, especially if they are in a row, that's enough. It will trigger the processes. So in general, it shows the much more vulnerability of permafrost even in even cold conditions. And of course, in warmer conditions, it's even more vulnerable. So I think I have one more point, but I have to think about it, and I may come back.
All right, thank you. We'll be opening this up to questions in a moment, and I should say that those of us joining us via webcast, you can type questions into the window below the webcast. We have an administrator monitoring that thread in the briefing room who will ask your questions. Please make sure you identify yourselves and your outlet, and if your question's for a particular panelist, please note that as well. And
I got my point.
Okay.
So that point is also very interesting. Say, of course, scientists know about this, that it's enough to get deeper active layer to start these processes. That's why scientists are measuring this summer thaw, so poking into tundra with metal sticks and measure this depth of thaw. And this already going on for a while, and it's even an international program, Circum-Arctic Active Layer Monitoring System, and so and so. But looking at the data, you see that there's a huge interannual variability. So one year you have deep one, and another is shallow one, and if you look at whole records, which already are like 15 years or sometimes even longer, there is not exactly clear picture of it. Not exactly. Well, it seems like it's getting warmer. I mean, deeper sometimes, and then, oops, in other several years, it's shallow again. So this kind of thing shows very kind of integrative point that it's really getting deeper. The summer thaw is getting deeper. Otherwise, it will not happen. So that's, I think, very, very important point. So even with all this, long-term records, and they're very useful, and exactly we will, in the future, we will compare what was now and what will happen in the future. It's very good reference. But this kind of integrative picture of now we can tell that at least at those sites which were described in this paper, active layer really get deeper during the last few years. Definitely, because otherwise it wouldn't happen. So.
Right, thank you. Our final panelist is Ken Tape.
So I study Arctic vegetation, and I think on behalf of the other co-authors who are plant ecologists in the Arctic, I would hesitate to generalize too much about the vegetation changes that are going along with these changes in hydrology. There's a lot of different types of ice-wedge polygonal ground. But I would say this, that Arctic vegetation is really in a fairly delicate balance with climate, soil moisture. And when I say climate, I don't just mean summer temperatures, but also snow depth in the winter and soil moisture in the summer. Those things really control, in a lot of ways, what vegetation is present at any site. And so what's I find really compelling about this work is that it shows that all three of those things are changing, right? So the sort of relief on the landscape is changing. That allows for greater snow depth in some places. For example, if you have an ice wedge that's thawing out, you start to get a little bit of a trough. Now suddenly you're accumulating a lot more snow in that position. That also makes for warmer ground temperatures. And then in the summer, because of these changes in relief, you have changes in drainage. And those changes in drainage happening all over the landscape are, affect vegetation. And the vegetation actually responds fairly quickly. One of the great things about vegetation is you don't necessarily have the problem with interannual variability that you have with, snow depth or active layer depth or water pooling, right? So if you have one cold year, it doesn't mean, or if you have one really wet year, it doesn't mean the vegetation totally changes at the site. The vegetation is more integrates at least a few years of those conditions. And so the vegetation is actually one of the first things that I think people picked up on, which led to, stimulated a lot of this work is, you'd go back to a site that you were at maybe 5 or 10 years ago, and suddenly what you start to see is all these water-loving sedges growing in these troughs that are thawing, right? So that's, I think if I could generalize about one thing, it's that, where you get the creation of these troughs, it gets a lot wetter, and the species that were there that get replaced by, well, let's say water-loving species, often sedges. That's sort of one example of how this can go. So, so yeah, I mean, you change the relief, you change the drainage, you change the soil moisture, and you change the snow accumulation in the winter. The vegetation is going to respond to that. But it's hard to say, you know, one area might get wetter where there's a trough, but the area in the middle of the polygon, if we use the muffin analogy, the area on top of the muffin, it gets a lot drier. And so, you know, you might have much wetter species here, much drier species in the center of the polygon, but there's a lot more heterogeneity than there was before. I guess that might be one thing you could generalize about. There's much difference, there's a much greater difference among these vegetation types in a really small area. So, guys have any thoughts on that?
Yeah, no, it's good that you brought that up, Ken, because we didn't plan to write this paper 50 years ago. But the data is coming from field sites where people have been working for several decades, and like you said, Ken, they've done observation that the vegetation has changed, and that's where we're starting seeing the same phenomena across the Arctic and put it together in one story. So.
And I think in a lot of ways the hydrologic work that we're putting out today is sort of a starting point for the vegetation work. I think just laying sort of the hydrologic and some of the geophysical groundwork will allow us to get into more of the complexity related to how vegetation is changing.
All right, thanks everyone. We'll open it up to questions now. If you've got a question, if you could please wait for the microphone so the folks on the webcast can hear it.
Hi there. I'm Matt Miller from KTOO in Juneau, and I wanted to see if any of you could explain whether the lack of moisture and the runoff has any sort of an effect on the heat retention or the energy retention of the soil, and whether that gets transferred to the atmosphere at all.
So changes in the soil. In the soil, yeah. Well, what we see, yeah, definitely there is some changes in moisture, soil moisture, like already was mentioned. It's became a little bit more spatially variable. So you start to see very contrasting troughs where there's water can actually standing even over summer, and then middle part of this polygons or muffins, which are getting really dry. This is kind of micro scale variability, but the question is, in general, it was addressed in the paper, that in general the surface is getting drier because of better drainage conditions. And as soon as surface is drying, then during the summer it will be less evaporation. So less evaporation will produce less moisture to the air, and it will change the even circulation patterns. So it is even if it's kind of looks very local, very small effects, but if this change is happening in a big enough area, so you can change the energy exchange and moisture exchange between atmosphere and the surface, and it will have some impact on the atmospheric circulation, and you can have, for example, less precipitation during the summer possible. And that was actually shown by using some climate models. So with this kind of exercises and see how sensitive our atmospheric circulation and moisture content in the atmosphere is to this kind of local process. It actually has some effect on that, yeah.
I would like to add one thing to that, is that the surface water used to be in these polygons very shallow, and it changes to deeper troughs. And so what happens is that the water temperature is decreasing in the process, which adds to the processes that Vladimir already discussed, is that even if you have open water, the temperature is slightly cooler, and so you'll have less evapotranspiration there.
I know you've explained this, but could you talk, like, basically how this all happens? In the summertime warm, but then you say that it still continues to be very cold soils or cold permafrost. And then also, is this like across the board in the Arctic, or are there certain areas that are more affected by this than others?
Right. Yeah, I'll start and then you can fill in, Vladimir. Yeah. So here we've looked at 11 sites across the Arctic where me and my co-authors have been to in person and worked at several years. And at 10 of these 11 sites, we saw this happening across the landscape. So, for example, if you take an aerial photography that is 500 by 500 meters wide, we saw this happening throughout that photo. On one of the sites, we only saw this happening in at one specific location. And that was at a site we think it still experienced the same warming air temperatures and still saw the same warming permafrost temperatures as all the other sites. But what we think is different with that site is that it had this protective layer above the permafrost. So this increased active layer that Vladimir was talking about had not really made its way down to the ice wedge yet. So it was buffered against this warming. I would say that we're seeing like a succession of polygon types in this landscape that then affects the hydrology, flow and storage of water. So we might start off with a completely flat, even surface where we don't see any surface features. Or we might start off with a landscape where we have these ridges and these shallow pools. So then imagine you have the muffin pan and instead of filling it with muffin dough, you fill it with water. That's kind of what it looks like. And then as we then have a really warm summer, we start melting the top of these ice wedges. And then we start forming these isolated pools of water that might become fairly deep, like a meter deep water. And if we continue that degradation of this ice wedge network, then we might connect one isolated pool of water with the other, and then the water can run off and you dry the whole landscape. So it's kind of 3 stages that we saw at these sites, both in the aerial photography and also site observations. And then the real world is very complex. There's a lot of pieces that are interacting. So that's why we use the modeling as to kind of simplify the landscape and say, if we have only this polygon type, what does it do to the storage of water in the landscape? What does it do to the runoff? And then if we have these other polygon types, what does it do to the hydrology and the surface runoff? So we were able to simplify it that way and show that going from the muffin pan with the water in the holes over to the ready muffins, that we're dramatically increasing the runoff from the landscape and making the landscape overall drier.
I can actually add to one part of the question was kind of why it could happen in the cold permafrost, so that's part of it. Well, this process is mostly reflecting summer conditions. And if a summer is getting even a little bit warmer, the active summer thaw layer is getting deeper. And eventually, if it wouldn't happen before, it's just first time, then you see all these processes. So it's actually also indication of it was not happening for the long time in the past. It's just happening right now. Now, if you're talking about permafrost temperature, of course you have to think about both summer and winter because it's integrating all year round. And winter is getting warmer. Actually, winter is getting warmer even faster than summer is getting warmer in the high Arctic. However, even with warmer winters, it's still minus 30 and minus 35. Well, instead of minus 40, it's minus 35. Well, it's still pretty cold, and winter are still very long. That's why if you average over the year, it will be minus 10 anyway. So maybe it became minus 10 instead of minus 12. But for permafrost itself, it's minus 10 is as good as minus 12, really. So that's the difference between what we see as a result of warmer summers and as a result of warmer in general years. We just measuring higher temperatures in permafrost, and we're measuring them. On the North Slope, it's actually warmed up by about 3 to 5 degrees Celsius during the last 30 years. So we see it, but it's still -5. So for permafrost, -5 almost as good as -10, almost, not exactly, but so that's kind of a little bit of controversy, but there is no.
My name is Caitlin. I'm with NOVA on PBS. Can you explain a little bit more about how pervasive these ice wedges are in the landscape, and the point being, like, what's the interaction between them as they melt, and also what their interaction is with permafrost in general?
Yeah, so we have, I'd say right now that we kind of identify that we need to do as a community is to get a good quantification of how large portion of the landscape actually has these ice wedges under them. We could look at vegetation maps and do an educated guess of what the coverage is. And it could be as much as 2/3 of the Arctic, but I think that's something we need to do, and we start to have the resources for it and the data sets for it. And these ice wedges, it's really a network of them across the landscape. So they form these polygons, ice wedge polygons. So these polygons have a diameter of 15-30 meters, and then they're surrounded by these ice wedges. And so if you melt the top of all of those ice wedges, then you're creating this channelized network in there. So, and then they're mainly ice. Like if you drill into it, it's white ice.
Yeah, just to illustrate, so in some places it's about 80 to 90 and sometimes even 95% by volume ice. Of course, it's extreme case. So in most cases, it's between 50 and 70% of excess ice on the landscape. But it's more ice than soil, actually. So in terms of, it's a very good point that we don't know exactly the distribution, complete distribution of areas with ice wedges, simply because you can see them if they are active, or they actively growing, you see that as a polygons, or if they are actively degrading, then you will see them again. But if they are not that active, you don't see it from the surface. And such areas very big actually in Alaska. Well, first of all, around here, so we know there's big ice wedges. If anybody of you, visited permafrost tunnel, you know there's huge of them and big one, but they're not growing anymore. That's why from the surface you don't see anything. That's the tricky part, to choose place where to build your house, right? Because you don't see them from the surface. But there is much more even area with ice wedges, like, for example, northern foothills of the Brooks Range, or all northwest of Alaska, where it's kind of hilly, tussocky tundra. You don't see them very well, but they are there. And you see them only when, by changes in hydrology and change in wetness of the surface, suddenly they start to degrade a little bit, and you see them. Wow, they are there. But before that, if they're stable, you don't see them. So really, it's I would agree, like at least one, what you said?
Canner in the corner.
No. How many percent? 2/3.
2/3, yeah.
Yeah, 2/3, except for some mountain regions. Of course, that's a little bit. But even in mountains regions, in all these intermountain depressions, you will see them anyway. So it's very common. It's the most common massive ice kind of form of massive ice in the permafrost regions. But there are some other forms as well in different parts of the permafrost. There is even more serious one, is horizontally oriented big masses of ice, about 10 to 12, sometimes 20 meters of thickness, and laterally going hundreds and hundreds of meters and even more. So, but this is even more. In this case, it's 100% of volume is ice. Yeah.
Hi, Sarah Dabowski, KTVF, Channel 11. What are some of, I know you kind of touched on it briefly, but what are some of the negative effects that can come from ice wedges melting? As far as like to people who live there or just anything in general?
Natural resources. You're responsible for that.
Okay, so the negative effects, the first thing that comes to mind is the uneven degradation of the ground. So if you build a road on this, you will find that this road becomes bumpy very quickly if the ice wedges are degrading. This we typically don't like. The other things, so we touched upon the carbon question, although I think it is still more of a question than we have answers for that. As the landscape gets drier, it is very likely that more carbon will escape into the atmosphere that was previously stored in permafrost. But I don't think we have solid numbers on that yet. The water, so we are potentially getting more fresh water in the rivers. This could be a problem as well as a resource because, well, some people are looking for water and other people are trying to drain the water. Take, for instance, the situation at the Dalton Highway right now with the flooding along near Franklin Bluffs. The Department of Transportation is working really hard to make sure the water doesn't get on the road, and this can be related to processes like we are discussing here today. More of that water ends up in the streams, and therefore the streams don't freeze quite as early, and therefore they can produce water throughout the winter. Other processes, wildlife. I think it was mentioned that some of the birds are foraging in the shallow pools. The shallow pools are disappearing. There's an example also of geese migrating further north, but maybe that's more your. You can talk more about that. Yeah, that's all I have.
Yeah, I would just reiterate what you were saying about carbon. I mean, carbon is probably and how permafrost degradation across what we're really talking about is, half of the Arctic, how that is going to affect storage of carbon, both in frozen permafrost soils, but also in the so-called active layer, just, seasonally frozen soils underneath the vegetation. It's not just we're not just talking about permafrost degradation, but also about increasing temperatures as the vegetation communities change, and in a lot of cases become more productive. The vegetation communities grow faster, grow taller, and I think the idea is that a lot of the carbon that's stored in the soils, because the soils warm up, that carbon gets mobilized and released to the atmosphere. I guess that's the concern, and I don't think we have an answer to that question yet, as Ronnie alluded to. But when you're talking about permafrost degradation, about across half of the Arctic, I think that's probably one of the biggest global concerns. That's not necessarily a problem unique to northern Alaska or the wildlife in northern Alaska, but how the carbon cycle is affected, is going to be really, really critical. So.
Yeah, I would like to add that this is very good about this direct impact. I mean, right now, how it's impacting, but you also can think about it as a kind of early warning, because it's just the beginning, and development of these processes can accelerate of thawing of permafrost, and we already discussed that it could be about 70 to 90% of material under your feet or ice is ice. Then losing this ice, you will really lower down the surface. And if you think about, okay, so we are talking about just few decimeter, like 30 centimeters increase of active layer. What if it will be 5 meters of thaw of permafrost? So your surface can lower by 4 meters, and if you have lots of ice. What means 4 meters? Well, if you look at the barrow, most of the elevation there is about 4 meters. See what I mean? So it's not just danger of local things, but you can lose the land to the ocean without even coastal erosion, just because water, the land in these Arctic lowlands is so low that any depression for several meters can actually allow to fill it with seawater. That's kind of more serious things.
Thanks, everyone. Appreciate it. If you have any follow-up questions for panelists, you can feel free to email them to Marmion Grimes. Her email address is on the main conference media page at ASSW2016.org/news/media. You can also reach the staffed press room at 907-455-2005. And thanks, everybody, for coming. Appreciate it.